So welcome to Math 383 Complex Analysis. So what we're going to be doing today is we're going to be finishing up a major unit of Fourier analysis. And so we're going to be talking about Poisson summation. We'll be talking about convolutions. We'll be talking about convolutions. We'll be talking about moment generating functions and some of their cousins characteristic functions. We will talk about the central limit theorem. We'll be talking about applications of Fourier analysis. Does anybody know what this is an image of and where this image is from? Have to speak everyone to say. What is this image and where does it come? It is from Star Trek: The Motion Picture. This might be the first time you really see some fun special effects for the Enterprise going to war. And this is in honor of the fact that this is going to be a warp speed lecture covering a tremendous number of topics. A lot of these really require 1 or 2 days. This is a graduate level class. My goal is to plant the flag to show you what's out there, and then you can carefully read the book. And if you want, I'm always happy to meet and chat about this. And as always, the journal item is the trying to find a good path through all the different algebra. So we talked about the Fourier transform last time, and we defined it as the integral of f of x e to the negative 2 pi I xy dx. We are going to use the negative 2 pi I as our normalization. There are 2 other normalizations, but we will not give them any space in this class. Okay, so we talked about if a function has sufficient decay, then good things happen. We do not need this. This is just so that I can be very lazy in which theorems I use, so that I can use Dirichlet's theorem. I debated giving you as an exam question to reprove Poisson summation under the weaker condition that just the function is, say, continuous and has sufficient decay with nothing about its first or second derivative, and just having you go through using Fourier's theorem rather than using Dirichlet's theorem. I think I've decided not to give that to you, but I haven't decided for sure if I've decided not to give that to you. So that is something to absolutely consider. Can you do something like this? Can you modify these arguments? I am deliberately not giving you a lot of homework so that you can explore stuff like this. So could you modify this proof if you had to? So the statement is that summing a function over the integers is the same as summing its Fourier transform over the integers. Why is this useful? Well, frequently the Fourier transform decays much faster than the function. And so you convert a long sum where it's very slowly decaying to essentially a short sum with rapid decay. So you typically don't need that many summands to approximate the value very well. And in fact, in many of the problems, just f hat of 0 is enough to essentially tell you what the value is. So this is Poisson summation. So let me just quickly sketch the proof. It's going to involve the function f of x is the sum and goes from -infinity to infinity of f of x plus n. And by the assumptions we're making, this function big F exists, this function big F is differentiable, this function big F is even twice differentiable, this function big F is periodic. We can use whatever the hell we want. Okay, this is like the fundamental theorem of calculus. If you assume enough things, you don't really have to use detailed results from analysis. You can use what they are. The mean value theorem, excellent, right? Our good old friend. The one with the mean value theorem, just keep hacking away with the mean value theorem. If you don't want to assume that the function is differentiable, not a problem, but then you have to go through uniform continuity. The arguments become a little bit more involved, but the result is still true. We are assuming so much that there is no problem in showing that this sum converges. We have sufficient decay on f. This function is differentiable. So f prime of x is going to be the sum and goes from -infinity to infinity f prime of x plus n. Wonderful. The derivative of an infinite sum is the infinite sum of the derivatives. We have enough decay so this happens. So now we can use Dirichlet's theorem. Dirichlet is one of the people where you have to be very careful when you say Dirichlet's theorem. So I should probably say a theorem of Dirichlet, lots of different theorems. This is that f of 0 is going to be the sum and goes from -infinity to infinity of f hat of n. Is that the function is given by its Fourier series expansion, where f of x is the sum of f hat of n e to the 2 pi I n x, and goes from minus infinity to infinity. Now, this wouldn't be a warp speed math class if we didn't overuse notation. And so here the hat is talking about the Fourier transform of a continuous periodic function on the interval 0, 1. Later, of course, hat will refer to the Fourier transform, it's referred to the Fourier coefficients of a continuous periodic function on 0, 1. Later, it will refer to the Fourier transform of a function on minus infinity, infinity. So we will overload notation a little bit. All right, so DRC-STEM says that if your function is differentiable, then the Fourier series converges pointwise to the function wherever it's differentiable. So if I just take x equals 0, I get big F of 0 is the sum of the f hats. Well, what is big F of 0? That's just the sum of f of 0 of n, right? So that's half of our result. So we know the sum n goes from minus infinity to infinity of f of n is big F of 0 is the sum n goes from minus infinity to infinity of f hat of n. So hopefully I have not dropped the term. So now let's study f hat of n. This is going to be the integral from 0 to 1 of big F of x e to the negative 2 pi I n x dx by definition. But what is big F? It is a sum of f of x plus n. So I can't use the same letter n because I'm already using n as the f hat of n. Unless I just do a quick search and replace and make all of these n's equal to m's, which is very easy to do. So it would have, but this way I'm using exactly what's on the book. And so this is then going to be the integral from 0 to 1. The sum n goes from, I'm sorry, n goes from minus infinity to infinity of f of x plus n e to the negative 2 pi I it's going to be mx dx, right? What do I want to do with the integral and the sum? So I want to switch them. But the other thing is, let's think about what's actually going on. X ranges from 0 to 1, and n ranges from negative infinity to infinity. What is the integral from 0 to 1, and then the sum, n goes from negative infinity to infinity? This is the same as what? Yes. Yeah, it's just the integral from negative infinity to infinity. Because you fix a value of n, so n equals 15. I go x plus 15 from 0 to 1, so I go from 15 to 16. And so I'm just going through the entire real line and stuff of size 1. So we get the sum, n goes from minus infinity to infinity of f of n is equal to the sum m goes from minus infinity to infinity of f hat of m, which is the sum m goes from minus infinity to infinity, the integral from minus infinity to infinity, f of x e to the negative 2 pi I mx dx. But what does that equal? The Fourier transform evaluated what point? It's the sum, m goes from minus infinity to infinity, of the Fourier transform of little m evaluated at the point m. And that finishes the proof of Poisson summation. Yes. Yes, I took away the sum. We have the sum of f hat of m goes from minus infinity to infinity. And then f hat of m itself is the integral of the sum. there's two sums in an integral. There's big F and there's little f. Big F is the sum from negative infinity to infinity of little f of x plus n. So I'm piecing them all together. So this is the quick proof of Poisson summation. And again, depending on how fancy you want to be, you can get into a competition with your friends to see who can prove it with the least conditions. I don't know if anybody ever saw the game show Name That Tune. You say, I can name that tune in so many notes. And the goal is to be the one who gets to name it, but you don't want to say you can do it in so few notes that when you hear it, you no longer hear it. Now, if I go, duh, what am I thinking of? Possible. I was thinking of something else. Beethoven's Fifth. But again, with just one note, it's done. I go da da da. By 4 or 5 notes, it's really obvious what I'm thinking of. At least if I can carry a tune somewhere. And so it's a game as to what is the minimum amount you need. And there are entire industries that go through and they try to weaken the conditions as much as possible. The first proofs often just assume the kitchen sink. Yeah, we'll throw everything at it. Everything's as nice as possible. And then you go through and you really carefully look and see, what do we really need here? Well, here I was using pointwise convergence. So for pointwise convergence, I need Dirichlet's theorem. Do I really need pointwise convergence to the Fourier series? Could I get by with the Fourier series, which converges pointwise uniformly? And maybe just try to work at a point where the function is continuous, but not necessarily differentiable. And so I will leave that as an exercise for you to think about, could you make this work in a case like that? Yes.
So we have the big F, we have the interval going 0 to 1, and for little
So for big F, it's the Fourier coefficient. For little f, it's the Fourier transform. This is what I mean by overloading notation. Okay. The worst I ever saw is in one of my undergraduate classes, a little f on one side was not the same as the little f on the other side. And once I realized that it was the Galois theory, I thought, oh, okay, now I understand what's going on. I thought the two f's were the same, but no. All right. So what I want to do now is just review a little bit of some stuff from probability. So we're going to start with what's called the moment generating function. Anybody who hasn't taken probability, do you want to guess what the moment generating function gives us? Every now and then math has good names. The moments, yes. Right? This function generates the moments. And what is the moment? The kth moment of a probability distribution is just the integral of x to the k times its density dx. This is the kth moment. And so it's defined as the integral or the sum. Will basically work in integrals in this class because I prefer integrals as the integral of e to the tx f of x dx. The moment generating function is related to the generating function. We don't really need to worry about that. What is the thing that worries you about the definition of the moment generating function? It might not converge. We have this exponential. For what value of t? Is there any value of t where this converges? Not necessarily. Well, actually, no, not necessarily. Because remember, x can be negative as well. So if t is 0, it makes sense because if t equals 0, then you're just integrating the density. And because it's a probability distribution, the integral of the density is 1. All right, it converges always when t equals 0. It is possible that that is the only value of t for which it converges, which means that the moment generating function does not always exist. Fortunately, it has a cousin, the characteristic function, which always exists. What do you think the characteristic function will involve? Given that this is a class 1 complex analysis. Yes. I. Yes. The complex. So basically, you replace t with it or 2 pi it or negative 2 pi it, depending on how you want to speak. The characteristic function is essentially the Fourier transform. So if I replace t with it or 2 pi it or negative 2 pi it, it's the Fourier transform. The Fourier transform will always exist if your probability is nice. And so we're in business now. Okay. So I'm not going to go through this in detail. If anybody's interested, you can look at the slide. if you do a Taylor series expansion of the moment generating function, if you expand out and go back to the definition and just take the function e to the tx and just write it as a sum of tx to the n over n factorial and say, oh, the integral of the sum is the sum of the integrals. When you do some algebra, you will then, as you expand it, you will get the moments of the probability distribution. Hence the name moment generating function. The next statement says if I take a random variable x with density f, and I consider a new random variable y, which is a linear rescaling, it's alpha x plus beta, the moment generating function transforms very nicely. And I've done the calculation on the side if you want to see it. The last one, and we'll actually prove this a little bit later, is the moment generating function of a sum of two random variables is the product of the moment generating functions. Or more generally, the moment generating function of a sum of n independent random variables is the product of the n. The simple proof, and I actually gave it away when I said it like this. How do you do the proof? Yeah, no, not hand waving. What kind of hand waving? What kind of hand waving? If there's time, I will show true hand waving after class as a special. This would embarrass my son. I will show the proof. What kind of hand waving is this? Yes, parentheses. If I know it's true for the sum of two, if I have a sum of n, we'll take n minus 1 and group them together. And now I have a sum of two things. And then you just keep repeating by induction. So in all of these proofs, it always comes down to the case of two. Once you know the case of two, the general case follows by a special type of hand waving, which can be justified, the parenthetical hand waving. All right. This is to just show you why real analysis is hard. Here are two probability distributions, and they have the same integer moments. This should not be the case. How many of you have heard of the paper, Can You Hear the Shape of a Drum? So if you know that paper, this is what makes it, oh, damn it. Okay? You should not have stuff like this. If I know the moments of my probability distribution, that should determine the probability distribution. Nope. I believe they have the same half moments as well, half integer moments, but if you go away from half integer moments, you actually see differences. What's really going on, if you want the moments to uniquely determined, you need the moments of two probability distributions to agree on a sequence of moments that accumulates. Okay, you should now be thinking of certain theorems from complex analysis. So that's why Miller's talking about this today. It all comes down to complex analysis. It all comes down to accumulation. This is why we can get certain results. This is what we need. It's not enough to have things hold at a sequence of integer moments or half integer moments, because those don't accumulate. You can have differences. But if it holds on a sequence that accumulates, we're in business. I can't show this distribution without showing, of course, the e to the negative 1 over x squared. We've talked about this many times. And this just reminds us that in real analysis, a real analytic function, well, what does that mean? It means it's supposed to be given by its Taylor series expansion. Here is a function which is infinitely differentiable. All the derivatives exist at the origin, but it is not equal to its Taylor series expansion. And this, again, just reminds you how different real analysis is from complex analysis, that we can have stuff like this happen. Right, so what I want to do now is I want to talk about convolutions and random variables. So imagine I have random variables x1 and x2 with densities f1 and f2. I can let the random variable x be x1 plus x2, which is the same as what? X1 plus x2 is the same as x2 plus x1. And again, I'm assuming here everything is independent. So what I want to do is I want to write down what is the probability density function for my random variable x. Hopefully I should have something nice in terms of f1 and f2. So what I could do is I could do the long way. What's the probability that x is at most little x? This is the cumulative distribution function of x, the CDF. And this would be the integral from minus infinity to infinity, f1 of t, f2 of x. One signature, I'm doing this correctly. One, let's go. X1 goes from minus infinity to infinity. X2 goes from minus infinity to x minus x1. F1 of x1, F2 of x2, dx2, dx1. So if I write it like this, I want x1 plus x2 to be at most little x. And so now no matter what value of x1 I have, since x2 is at most x minus x1, their sum is going to be at most x. So this is going to be the cumulative distribution function, the probability I take on a value at most little x. The way you find the density is you take the derivative of the cumulative distribution function. So the density of the random variable x would just be the derivative of this with respect to x. Okay, so we have d by dx, the integral x1 goes from minus infinity to infinity, the integral, okay, well, f1 of x1. Now for the second one, I integrate from x2 goes from negative infinity to x minus x1. That's just going to be the antiderivative of the function f2, I'll call it big F2, evaluated x minus x1. I should, of course, subtract off the value of it at negative infinity. But what's the value at negative infinity? 0, because little f2 is the density, big F2 is the probability you take on a value at most that. The probability that I take on a value at most negative infinity. Okay. And what's wonderful about this method is as soon as you see the antiderivative, you should be worried because in general, we can't integrate. This is different than you can't get credit for taking classes that teach you to integrate. That's something else I'm venting on. You can't integrate a general function in closed form. We just can't do it. But immediately after we integrate F2, what do? We take its derivative. And of course, what's the derivative of an integral? The integral of the derivative, without a doubt. So this is just the integral x1 goes from minus infinity to infinity, f1 of x1, and then we have the derivative of f2, that's going to be x minus x1, and then we have to take the derivative of the inside x minus x1 with respect to x1. What is that equal to? So the derivative, we have to use the chain rule. It's f2, big F2, evaluated at x minus x1. What's the derivative of x minus x1 with respect to x? 1. With respect to x. 1. I'm taking the derivative of x minus x1 with respect to x. x1 is constant, so technically I need to just write times 1 dx1. And so here's an explicit formula for the density of the sum of two random variables. And we call this the convolution. So we would say that this is f1 convolved with f2 evaluated at the point x. I could have just informally hand waved and said this is the answer. I want to calculate what is the probability the sum is little x. Well, if the first variable is x1, then the second variable has to be x minus x1. And I just take the product of their probabilities and I just integrate over all possible choices for x1. It's a very reasonable answer. But this must be the same as f2 convolved with f1 of x. One way you could see this is, of course, you could just do a change of variables. The other way is to say, well, x1 plus x2 is the same as x2 plus x1, so it follows immediately. So what we've just seen is the density of a sum of two independent random variables is the convolution of the density. This tells us that when we're studying random variables, when we're studying these density functions, convolutions are going to be very important. Have we seen anything that's used convolutions before? Yeah, FourierTransform. We've used it when we were proving things like the Bayes theorem or Dirichlet's theorem. We had convolutions. We had this approximation to the identity. So this is telling us, maybe these subjects are actually tied together. Complex analysis is not a class that should be compressed to one semester. Even at 2 semesters, there's far too much material. Some of you actually met one of my 2 complex analysis professors at a conference recently. He taught the second semester, the super advanced topics. And there's just so many things to go through. At this part of the semester, I am deliberately not overloading you on homework. I want to show you what's out there. I want you to have a sense of what can you do with complex analysis? What kind of problems is this useful for solving? You should get used to asking certain questions when you see objects. Yeah, I'm not going to say what questions you ask when you see a group, because I don't really do that, but can somebody give me at least one question you should ask when you see a group? Is it abelian? Is it finitely generated? What can you say about its subgroups? Is it normal? There's a bunch of questions you can ask about a group. If you see a probability distribution, what's the first thing you want to ask about the probability distribution? I'm sorry? No, we're assuming you know what a probability distribution is. All right, so probability distribution is it's a function that's non-negative, integrates to 0. We're going to just look at continuous probability distribution. What's the first thing you might ask about a probability distribution? That's a really specific first question. I mean, that's a little personal. Try to do like the little dance and work your way up to that. What's a smaller question you might start with? Yes. Almost. So your question assumes that there's a mean. But I will accept that, what's your mean? And after you find out the mean, if you want to know a little bit more to see if you're compatible, what might you ask? Well, that's going for the, with baby steps. After the mean, what would you go for next? Standard deviation, variance, second moment, and then you might jump ahead to, what's your moment generating function, right? And the hope is, of course, the moment generating function would uniquely determine the distribution, but that is not always the case. One of the things that might be useful to talk about when we look at a function, such as the density, is what is its Fourier transform? So this is the notion of duality, that sometimes it is easier to study a problem in a related space. So look at a tweak of a problem. We talked about the chess problem earlier, putting down 5 queens on a board, on a 5x5 board, such that 3 pawns are safe. It's much better to look at the dual problem, put down 3 pawns so that there are 5 squares not attacking. This is one of the most valuable ideas in all of mathematics. So sometimes rather than looking at the original problem, you can do some kind of transformation and make it easier to study. We are going to look at the Fourier transform of probability density. And then, of course, the question is, how do various things relate under the Fourier transform? So you could ask, what is the mean? How does that change if we do a Fourier transform? But looking at this, what is the natural operation to do to 2 probability densities? Convolution. So a natural question to ask is, the Fourier transform of a convolution is the natural thing to guess. No, we did not. We didn't. I know what the answer is, and so I know we did not prove that, because that's not quite right. It's close, but it's not quite right. We know the derivative of a sum is the sum of the derivatives, but the derivative of a product is not the product of the derivatives. You have a more complicated formula. This suggests we might want to study the Fourier transform of a convolution. So let's see if I can do this correctly. Let's let f be f star g. Let's do f1 star f2. Okay. We want to calculate f hat versus, say, f1 hat and f2 hat. Right? We want to see, is there a nice way to express the Fourier transform of the convolution in terms of the Fourier transforms of the constituent parts? All right, let's go through things very slowly. So f hat of y is the integral from minus infinity to infinity, e to the negative 2 pi I xy, f of x dx. Normally I write f of x e to the negative 2 pi I xy. I wanted to write the exponential first. Why did I want to do that? Well, because I'm about to replace f with the convolution of f1 and f2. So this is then, let's just be very clear. This is an integral x goes from minus infinity. So this is the integral x goes from minus infinity to infinity. And the integral, let's say t goes from minus infinity to infinity, e to the negative 2 pi I xy f1 of t, f2 of x minus t, dt, dx. Okay. I want to calculate Fourier transforms. So if I have an f1 of t, what does f1 of t want to be hit with to get a Fourier transform? The final variable we're going to get at the end of the day is y. So if I want the Fourier transform of f1 of t, what exponential would I want to hit that with? Yeah, so this wants e to the negative 2 pi I ty. And what does this want? E to the negative 2 pi I x minus t y. And this is e to the negative 2 pi I x minus t plus t times y. Right? I have done nothing yet again. One of the most valuable things we can do. Why is this useful? Well, now I can write this as the integral. Let's go, t goes from minus infinity to infinity. I don't mind switching orders of integration. And now have f1 of t, e to the negative 2 pi I ty, integral x goes from minus infinity to infinity, f2 of x minus t, e to the negative 2 pi I x minus t times y, dx, dy. What does the x integral give us? Yeah, f2 hat at what point? Nope, that's at y. You just change variables, let u equal x minus t. The second integral is just f2 hat at y. And what's the first integral? f1 hat of y. So the convolution, so the Fourier transform of the convolution is the product of the Fourier transforms. Wow, that's nice. The Fourier transform converts integration, hard, to multiplication, relatively easy. This is one of the reasons why we absolutely love the Fourier transform. Instead of doing integration, you now just do products. Now, at the end of the day, what do you think you need to do? I'm sorry? Go back, you need to take the inverse Fourier transform. And that's where complex analysis comes back again, is we have to do the inverse Fourier transform to return to where we want. But this is the general idea. Shift to the Fourier transform space, convert integration to multiplication, solve the problem, and then convert back. Okay, so the characteristic function of the standard normal. So we're going to define the characteristic function of a random variable x at t to be the expected value of e to the negative 2 pi I tx, which is the integral from minus infinity to infinity, e to the negative 2 pi I tx f of x dx. So this is the characteristic function. And again, there will be slightly different definitions depending on which book you look at as to whether or not you have the minus sign and whether or not you have the 2 pi. It does not matter. It's just a simple rescaling. The key fact is that we have the I. And because we have an I, I'm allowed to talk about this in a complex analysis class. It is absolutely a legitimate topic. And it's going to be useful because it converges. So we've talked about why this converges. So converges as above as absolute value 1. So because it has absolute value 1, this integral converges. Okay. So we want to calculate the characteristic function of the standard normal. The central limit theorem says if you have a sum of independent, identically distributed, nice random variables, then their sum converges to being normally distributed. If you standardize, if you subtract the mean and divide by the standard deviation, it converges to the standard normal. The way we're going to prove this is the following. We look at the characteristic function of the sum, and we show the characteristic function of the sum converges to the characteristic function of the normal. So if the characteristic function converges, the characteristic function is the Fourier transform of something. So the hope is that if the characteristics function converge, then it's the Fourier transform of something which must be converging to the density of the normal. And that's where you now need to use the inverse Fourier transform and justify it. So the idea of today is to give you a quick sketch of the proof of the central limit theorem. Okay, so we want to calculate the characteristic function of the standard normal. So we need to integrate from minus infinity to infinity of 1 over square root of 2 pi e to the negative x squared over 2 e to the negative 2 pi I x y dx. And that will be the Fourier transform of the standard normal at y. We could do this integral. It's a little bit of a pain, but we could do it. Why is this a pain? Well, because we have to now do some kind of complex integration. Much simpler is to study instead the integral from minus infinity to infinity, 1 over square root of 2 pi e to the negative, I'll just do xy dx. Oops, I dropped the e to the negative x squared. E to the negative x squared over 2. So this is just the integral from minus infinity to infinity, 1 over square root of 2 pi e to the negative 1/2 x squared minus 2xy plus y squared minus y squared dx. I just completed the square. Can we handle this integral? Yeah. This is just going to be the integral from minus infinity to infinity, 1 over square root of 2 pi e to the negative x minus y squared over 2. And I have an e to the negative 1/2 negative y squared, that becomes e to the y squared over 2. So I can pull out an e to the y squared over 2 dx. What does this integral equal? 1 over square root of 2 pi e to the negative x minus y squared over 2. Yeah, it's the standard normal. Its integral is just 1. So we just get e to the y squared over 2. What did we do? If you think about it, this is the characteristic function evaluated at what point? Not y. So think about it really carefully. Nope. So we have e to the negative xy. We're supposed to have e to the negative 2 pi I xy. So in some sense, y is equal to 2 pi I y. Right? So what I'm really doing is I'm evaluating it y over 2 pi I believe. Because if I now put that in my definition, the 2 pi I is canceled, where y is real. So we calculated the characteristic function of the expected value when we evaluated y over 2 pi I with y real. I want to do this for arbitrary y. Can I drop the restriction that y is real? Why? I'm sorry? Points of accumulation. So use points of accumulation. So we now have the result in general. And again, this is just another chance to emphasize how wonderful the theorem on points of accumulation is. Instead of having to deal with a complex exponential integral, we could just say, well, you know, if we change things and just consider so that we have a real argument, it's just complete the square. It's just the standard normal. We know that integral is 1. We now have the result. They agree on a sequence. You just have to show that this integral converges no matter what value of y I put in. Doesn't matter. Even if y is pure imaginary, so that e to the negative 2 pi ixy could be growing, it's at most growing exponentially, like e to the constant x, which is going to be killed by e to the negative x squared over 2. So you can show that this is going to be fine for all values. So the Fourier transform or the characteristic function of the standard normal of a Gaussian looks like another Gaussian. The only thing that you have to be careful about is depending on how you normalize things, you're going to have terrible factors of 2 pi. Does this give you some sense of why people don't want to put in the 2 pi up there? And you might want to just do e to the it or e to the negative it. Because then you wouldn't have to worry about putting in these 2 pi's. In rationalized MKS units, who are my physicists, what is the speed of light?
300,000.
No. In rationalized MKS. What's the speed? Yes. It's 1. And what's the gravitational constant? 1. Right. You basically adjust your unit so that all of your constants as much as possible can be 1. What about the fine structure constant? Yeah, that does not change. That's a fundamental quantity, unit independent, really good physics there. But you adjust things to be 1. In mathematics, we don't quite have the rationalized MKS units. We have 2 pi equals e equals 1. Sometimes you include square root of 2 equals 1, and you basically say, in everything that follows, it's correct up to factors of 2 pi and e, maybe square roots of 2, and maybe negative signs. All right, so now we want to prove the central limit there. So let's say we have x1 plus xn, and I independent, identically distributed random variables. Let's let x be the sum. The density of x is just going to be the density of x1 convolved with the density of x2 convolved with the density of xn. But if they're all the same function, it's just the same density every single time. And now if we take the Fourier transform at some point, that becomes the product, k goes from 1 to n, of the Fourier transform of each one at some point x. And then the hope is to show that this converges to the standard normal's moment generating function, or characteristic function. And the idea is, if the characteristic function is converging to the characteristic function of the normal, then the density, which we're taking the Fourier transform of, must be converging to the density of the normal. Else, how could the characteristic? So we then need to just do an inverse Fourier transform. So what we need to do is we need to look at x. So let's say each xi has mean mu and standard deviation sigma. And the expected value of the sum is just going to be the sum of the expected values. If you haven't seen probability like this before, it's okay. The expected value of the sum is the sum of the expected values. If each one of them is mu and I have n of them, what should the mean be? It should be n mu. And then the variance of a sum is the sum of the variances. It should be n sigma squared. So the standard deviation of x should be sigma square root of n. And so what we should really study is we should study z is x minus n times mu divided by sigma root n. This has mean 0 and standard deviation 1. And what you notice is that, well, if I want to look at I can write this as basically alpha x plus beta. And we talked earlier at the start of the day that if I have the moment generating function of alpha x plus beta, it's very nicely related to the moment generating function of x. I rescale the t, I rescale the argument, and I have an exponential factor outside. The moment generating function is coming from taking the expected value of either the tx. The only difference with the characteristic function is I'm letting t be negative 2 pi I t. So the same result is going to hold, and you're still going to have a result like this. And so essentially, the rest of the proof is done by now showing that I want to look at the Fourier transform not of x. I want to study the Fourier transform of z at x. And then you just go through and then you do the rest of the algebra. And when you expand everything out, you then see after doing some algebra that it's going to converge to the characteristic function of the standard normal after doing some algebra. If anybody's interested, I will post a video that goes through and does the algebra. The remarkable fact about the central limit theorem is it only depends on the first two moments of the distribution. I standardize by subtracting off the mean and dividing by the standard deviation, and then in the limit, everything is nice. What happens is when you look at this product and you expand it, you basically have something to the nth power. And the higher moments come in as lower order correction terms that affect the rate of convergence. So, again, the goal today is to just give you a rough sense of what tools come into the play. There's now some algebra. When you go through the algebra, you will see that the higher moments do not affect what the main term of the limit is. They only affect how rapidly you converge to them. And so this is to give you some sense of the power of complex analysis. So I want to just end with one quick note on other things you can study with the Fourier transform. You can study differential equations. So we can look at this beautiful result. If g of x is f prime of x, and h of x is x times f of x, then the Fourier transform of g is 2 pi I y times the Fourier transform of f of y. And the derivative of the Fourier transform of f is negative 2 pi I times the Fourier transform of h of y. So let's think about what's going on. It's converting multiplication to differentiation. If I look, g is the derivative of f, but the Fourier transform of g is multiplying f by y. Which would you rather do, multiply or take the derivative? Multiply. And so if you have a differential equation and you're trying to solve it, and you have something involving derivatives, if you take the Fourier transform, now instead of having derivatives, you now have multiples by a polynomial. And then the problem is when you try to solve it, at the end of the day, you need to find the inverse Fourier transform. And the hope is that if I have a function, it would be wonderful if there's only one thing that could have been sent there. You don't want to have multiple things being sent. How many of you have ever heard of the Caesar cipher cryptography? So you move every letter forward by a fixed amount, usually 3. One of my favorite quotes is the Caesar cipher really wasn't needed because so few people could read. Just writing down the message was essentially enough. If you don't know that I'm moving things by 3, how hard is it for you to crack? How long will it take? How many things do you have to try? 26, or if you assume I'm a little bit clever, 25. Assuming that I'm at least encrypting the message and shifting it, right? There's not that many things to try. If you had multiple letters going to the same letter in encryption, that would be bad. Because then you wouldn't know how to invert. If I then see, if both C and Q both go to W, if I get a W, I don't know, was it a C, was it a Q? So you need to have this nice one-to-one. And so the difficulty is, can we take the inverse Fourier transform? Will that be unique? Or can several different functions have the same Fourier transform? We just saw that the sequence of moments is not enough to be uniquely specified. The following is one of my favorite problems. I use this when I teach cryptography. So we all agree that the Caesar cipher is not that secure. What if I decide to spice it up a little bit? I'm going to choose 100 different shifts. And I'm going to encrypt your message by doing the first shift, then the second shift, then the third shift. There's 25, 26 choices for each. So that's now 25 to the 100 possibilities. That's astronomically large. Yes. I'm sorry? No, but I'm not doing all of them at once. I'm only sending you the final message after I do 100 shifts. I do 100 shifts, one after the other. There's at least 25 to the 100 possibilities. Is this secure now? You go through, you said you could go through 25, 26. Can you go through 25 to the 100? You don't need to. Why don't you need to?
The end result is your shift.
Yeah, the end result shift happens. The end result is I've just shifted it by some number. There's still only 25, 26 possibilities. This is one of the reasons why cryptography is hard, is you might think you're being very clever and you have a really nice way, and somebody might be, oh wait, actually, you can bypass all of that. I don't need to know all the intermediate steps. I just need to get to your final result. And so this is just something to be thinking about when you're doing these calculations. When are things unique? When are there multiple ways to get there? How can you get there? But this hopefully gives you some sense of why we care so much about the Fourier transform. All right, so this is a good place to stop. Have a great weekend all. Well, let me stop.